In this chapter, we're going to be talking about the limit process, the notion of limit and finding limits. But I'd like you to know where that limit idea fits into the notion of calculus in general. What is calculus? That's the topic for this section. Calculus is really the mathematics of change, and I'd like you to read about it a little bit in your textbook. There's a really neat discussion about what calculus is in the first couple of pages of this section. And there are some illustrations in that area that will help you understand the transition from pre-calculus to calculus. Now, the notion, as I said, is that it's the mathematics of change, and what's involved here is a study of tangent lines and slopes and areas and volumes and arc lengths. But although these items have been studied before, they're going to be studied in a somewhat different way. Now, calculus, as a mathematics of change, you might be thinking, what does that mean? Well, it's kind of like, you know, in pre-calculus, if we were studying some aspects of the flight of the space shuttle, for example, we can make some awfully good calculations about what's going to happen when the rockets stop firing. You know, if we're talking about dropping the solid rocket boosters and the rocket boosters are no longer firing, we can tell all kinds of things with vector analysis, remember, using some trigonometric information and some formulas. We can tell, for example, if we're going at a certain angle and a certain speed and those rockets go off, then we can tell all kinds of things about how much higher will the rockets fly, and how far downrange from that point will they be, and how long will it take for them to hit the ocean, and all sorts of stuff like that. But we can't tell anything about aspects of the flight of the space shuttle while the rockets are flying. That's where calculus comes in. That's the great power of calculus. We know all kinds of things about velocity if we are using calculus, you see, and those rockets are going off. So that's what we're trying to get to in this process. All right, now the jumping off point, the middle ground here between our pre-calculus and calculus is the limit idea. It jumpstarts a lot of different kinds of discussions. From the algebra and trig involved in pre-calculus, we go through this limit process, and all of a sudden we arrive at calculus and we perform tasks such as derivative and integral. These are really the basis ideas within calculus. Now, let me talk to you a little bit about the limit process and just kind of introduce you to what's in store for us. Why is this important? There are two classic problems that are going to be revisited here in the very near future having to do with this limit process. Now, after we discuss limit, we'll come back to these classic problems, but I just want to tell you where we're going. One of the classic problems is called the tangent line problem. And the tangent line problem is this, that you know, in algebra we talk about slope, and we can talk about the slope of a line. That's pretty easy. And that slope of the line corresponds to a rate of change. Great. But what happens when the line is curved? What happens if it's not a straight line? You see, what if it's a curve? How do we talk about change? How do we talk about slope? Well, slope is related to a line which is tangent to the curve at a particular point. Now, suppose I have a point P here, and I want to talk about the slope of this tangent line. Well, how do I calculate that? I mean, we know how to calculate slope if we have the coordinates of a couple of points. Okay, so let's talk about that. Let's create another point on this curve. Certainly, if we have a function here, we have this graph, we can find the coordinates of that point. We can trace to that point, for example, on our graphing calculator and find the coordinates of the point. Let's call the point Q. And so we could say, well, if we have a point out here that's Q, and we have coordinates of that point, and we have coordinates of this point, then certainly by using our slope formula, we can find the slope of the tangent line. We can even find the equation for the tangent line if we want to. Okay, great. Now, but does this tell us something about that? Well, not exactly, but it's an approximation, and if we make Q come a little bit closer, you see, if we put Q in this position, then we have a closer approximation. Well, what if we come even closer? We have a closer approximation, you see, by using closer and closer points. Now, how close can we get? That's where the limit idea comes in. We want make this calculation or consider the idea as Q becomes infinitely close to P in this situation. And if we talk about approaching P with Q, take Q and approach P, it is the limit as Q becomes infinitely close to P that will give us this tangent line, the slope of that tangent line at that particular point. So anyway, we'll revisit the problem a little bit later and we'll learn a great deal more about it. But incidentally, this line, if we're talking about a couple of points, is called a secant line. And we're just making that secant line, you see, be a better and better approximator of the actual slope of the tangent line at that point. And it turns out by using limit, we can get an exact value. Here's another classical problem. It's called the area problem. And the problem is to select an interval on our x-axis. And let's say the interval is from this point to, let's say this point. So let's call this point A and this point B. And in that interval, let's say that we want the area under this curve and above the x-axis and between these two points. So these are like endpoints of an interval, and we want the area under the curve and between the points. So we want, let me see if I can get this relatively straight here. Something like that. It might be leaning a little bit in one direction or another. But we would like the area under the curve, you see, and above the x-axis between these two dotted segments. So, well, how do we do that? Well, we know something about formulas for area. We know how to calculate the area of a rectangle, for example. Length times width. Okay, good. We have a length here between A and B. We can certainly make the calculation of that distance. Good. Now we have this vertical distance is pretty easy. It's just f of A, you see. F of A is that y value. So we can say length times width. And do we have then, you see, by thinking about the area of that rectangle, do we have the area under the curve? Well, no, we're not including this area, and we are including an area in here that is not part of the area that we want. So this is, although it's an approximation, it's not a very good one. So we might say, well, what if we increase instead of using this one rectangle, suppose we use more than one. Suppose we use 2 or 3 or 4. If I choose a point here, for example, and I think, well, let's see, if I choose a point right in the middle, then I have 2 rectangles. Well, this rectangle, gee, if I go from here and consider that and then consider this, I'm not, or this, you see, and then this one, I'm still kind of messed up. I'm a little more accurate if I make more rectangles. And the more rectangles I have, the better the approximation of the area under the curve. And then you might be saying, well, gee, which side of our interval, our little interval here, are we going to decide to make for our vertical distance? Now, for this, it doesn't make any difference. We have about the same on both sides. But in this, for this rectangle, gee, do we make this the top part, or do we make this the top part? That's a little bit of a dilemma. The idea, though, is that as we increase the number of rectangles, then we increase our accuracy on the approximation of our area under the curve. Now, let me consider, just for discussion purposes, that we're using the left side of the interval. Like this little interval right here, I'm talking about that rectangle. For this interval, I'm talking about this rectangle. For this interval, I'm talking about, let's see, if I'm using the left side, that's here to here. So I'm using that. So in this interval, I'm talking about here to here. In this interval, I'm talking about that. In this interval, I'm talking about this. In this interval, I'm talking about this. You see, so I've got a number of rectangles, and I add all of their areas, and I'm getting an approximation for the area under the curve. Now, the notion of limit allows us to increase the number of rectangles without bound. Without bound. So we're talking about an infinite number of rectangles here. And when we go to that number of rectangles and make this calculation, we have, boom, an exact value for the area under that curve. So that's what limit is going to do for us.